you a brief summary regarding what we have seen in the morning session. So in the morning session, we have discussed the specificities and difficulties which are related to solving mixed integer bilevel linear programs. Where are the differences and counterintuitive examples related to, compared to solving classical MILPs, or even compared to solving two-stage optimization problems like in stochastic or robust optimization. And then we moved on by introducing some simplifying assumptions. Two of them are important ones, that the HPR region is bounded, and the other one that the linking variables, those variables that link the leader and the follower, have to be discrete variables. Under these assumptions, I have shown you how to develop a finitely convergent branch and bound method. And then we went on with how can we improve this branch and bound by adding valid inequalities to deal with the trade-off between branching and cutting, with the trade-off between having a tighter formulation versus explicit enumeration. And so I showed you one basic family of intersection cuts that we have derived recently with my colleagues, Matteo Fischetti, Michele Monaci, Marco Sinel. And in the rest of this afternoon session for the part 2, remember we have 3 parts. So for the part 2 now, I will show you a fully fledged branch and cut approach with additional techniques, with a few more ideas for deriving intersection cuts, for the pre-processing, and for deriving additional valid inequalities based on the properties of the follower. And then in the part 3 today, this afternoon, we will move into developing more specific branch and cut algorithms, which are not valid for the generic bilevel MIP formulations, but only for the bilevel problems with interdiction structure. So more on intersection cuts. So the last, what we have seen at the end of the part 1 was this result. And this was the result establishing a convex set for which we know that there are no bilevel feasible solutions inside. This convex set is intersected with the HPR relaxation, and by taking the corner polytope, cone of the LP relaxation and intersecting it with this bilevel free set, we can derive a valid inequality to cut off the current optimal solution of the HPR relaxation. But remember that there could be many different ways of defining these convex sets, which are bilevel free or feasible, free of bilevel feasible solutions. And the point is that the bigger this set is, potentially, the deeper your intersection cut will be, the stronger the cut will be. You will be able to cut off more from the HPR relaxation. So what could be, I will now show you 2 alternative ways to deal with this situation and to derive additional convex sets to do so. The idea of the definition of this bilevel feasible free set comes from the work of the PhD thesis of Su and from their paper on the watermelon approach. And it looks like follows. I'm giving you as an input parameter a direction in which you can improve the objective function of the follower. That's why we call it delta y hat. And so if this direction is such that when you plug it into the constraints of the follower subproblem, the solution that you obtain by taking any point y and moving in this direction still remains feasible, then this guarantees you that there are no feasible bilevel points inside of this region. So again, once you know this, the delta y hat, this is a constant. So these are linear inequalities. A bunch of linear inequalities gives us a convex set. Now to understand, the proof is really given in these 2 lines to understand what is going on here. So first of all, what is this point delta y hat? This point is such that when you add it to the objective function of the follower, you are improving the objective. You remember we are minimizing. And at the same time, this point also satisfies all the integrality constraints. So the proof that there are no bilevel feasible points in this region goes by contradiction. So you simply say, okay, let us assume that there is a point in this set such that it is bilevel feasible. Let's call it x tilde and y tilde. But then, because by moving this point, I'm back. It seems that we had a problem with the internet connection. Can you hear me?
Yes, now I can hear you again.
Okay, great. Sorry for that. So I'm back. And so basically, by contradiction, you are showing that there is another feasible point in this region with a strictly better objective function. Remember that the optimal follower, the bilevel feasible points are only those that minimize the objective, so the original point cannot be optimal. So as you see, this set looks a little bit differently than the previous one. And of course, again, the question would be, how do we determine this point delta y hat? And this I will discuss in a few minutes. Basically, you will need to solve an auxiliary mixed integer linear program to find this point. And in both of these definitions, as you can see, we have this trick of adding +1 on the right-hand side to avoid that the bilevel infeasible point is on the frontier of this set, of the bilevel free set. And for this, we have to assume that the constraints are such that they can take on only integer values. There is another way to work with situations in which we can omit these constraints. So we can work even if the follower is a fully continuous problem, so we don't have to impose the restriction on the integrality of these values. And in this case, these cuts have been introduced in our work in Operations Research 2017. In this case, we can basically say, okay, if there is a point in which we fix the coordinates of the linking variables, we can evaluate this point, we can store it in the solution pool, and after that, we can get rid of this point by introducing intersection cuts related to the hypercube around this point. Why? Because remember from our story from the very beginning, it is sufficient to evaluate and to enumerate all possible combinations of the values that the linking variables can take. So once we have evaluated this solution, we can eliminate it. And we know, because the values are integer, that +1 and -1 around this point, there will be no other bilevel feasible points. Okay, so basically for separation of these cuts, the only thing that you need is the point x star that you will be encountering in the branch and bound search. So there is no NP, there is no additional auxiliary MLP to solve except the one to evaluate the value of the point with these coordinates. So when we talk about the separation of intersection cuts, now to summarize, we have several ways to do that. So remember our original set that we have started with, we said one possible way to do it is you have a point which is infeasible, you evaluate phi of x, and the optimal solution of this auxiliary MLP is the point y hat. So intuitively, if you think of the convex set bilevel free set S that we are generating in this way, it means that you are actually looking for a set that maximize it. It goes as deep as possible in the direction of the objective function of the follower. So in a sense, there is an infeasible point, which was the point, the high point relaxation optimal solution. And now you go down into the direction of the follower and try to find what is the furthest point, y hat, in this direction, which is bilevel feasible. And then the whole region in between you cut away. However, this is one strategy. The other strategy would be, why don't we try to find another point which defines this set, but in such a way that we get rid of redundant inequalities? Because right now, at the moment, we have in this definition of the set, the whole explanation, the description of the follower subproblem. However, it can happen that some of these inequalities are redundant for the definition of the bilevel free set. So instead of having this strategy 1 that we call separation 1, we could solve an auxiliary MILP in which we would try to get rid of as many hyperplanes defining the follower subproblem as possible. Why would we do that? Remember, because the bigger the set S is, the tighter, or let's say the deeper, will be our intersection cut. And so you can think then of solving an auxiliary MILP. I'm really not going into these details. The only thing that I will point out here is the binary variable W, which tells us whether the inequality from the description of the follower subproblem is redundant or not. And so if it is redundant, then Wi is 0. So we want to minimize the number of inequalities that will stay in the description of the set S. So by doing so, we obtain another bilevel free set, which satisfies these properties, but with respect to another bilevel follower's feasible point, y hat. And the third way comes from the results of Su and Wang, from their description that they used for developing a watermelon algorithm for the multi-disjunctions. So their idea is the following. Again, we will have now auxiliary variables t, and the variable t will take the value 0 if the facet can be removed. I mean, facet, we abuse a little bit the notation. When we say facet, we mean the hyperplanes describing the follower subproblem. So we have here again the example of Moore and Bart. And remember that all these 4 facets here come from the follower subproblem. And now if I want to remove this bilevel infeasible point, their idea is to take these facets and to translate them in the improving direction of the objective function. So again, delta y should be such that it improves the objective by at least 1 value. This is the first constraint. Again, we assume here that the coefficients d are integer. So it improves it by at least 1. And then in this improving direction, when we translate these facets, then the value of t is measuring by how much we have to translate them to make sure that after this translation, there are no bilevel feasible points in what remains. So we translate this facet up, we translate this facet to this direction, but we notice that translating these 2 facets is completely unnecessary because on this side of the hyperplane, there are no bilevel feasible points at all. And so, again, in a similar way, we try to get to minimize the number of faces that will be needed to describe the bilevel free set, which we call now X. So that's the intuition behind. So for each of these intersection cuts, obviously, you find the bilevel point. First thing that you do is you find the value of the phi of x. This is one MILP. And the second thing that you do is then after that, when you realize the point is infeasible, then you solve another MILP that gives you a the bilevel convex set, and then you intersect it with the current LP cone and you derive the cut. Okay, so this is the whole story about the intersection cuts. And remember, they are here in the basic branch and bound procedure, mainly to tighten the formulation and to improve the bounds. And now the next question would be, if we want furthermore to improve the branch and cut procedure, what else can we do? And one thing is the pre-processing that can be done at the follower level. And as I mentioned, this is a procedure that can be also done even if the follower is a pure linear program. The idea is relatively basic. So you look at the following. You look at this parametric follower subproblem for a given value of x star. And if the coefficients next to the y variables are all positive, or in theory you could also say strictly non-negative, and at the same time the contribution in the column B of this variable in all the constraints of the follower is also non-negative, then it is clear that in any optimal solution you will fix the value of this variable to the given lower bound. Okay, now the constraints are separated based on the bounds of the variables and the other constraints. Okay, and if this is the case, then this really doesn't depend on the value of the leader. And in this case, the value can be fixed both at the leader and at the follower level, which means that we can carry over these constraints into the high point relaxation. Similar situation you can do, of course, with the upper bounds as well. And one important thing here is that because of dealing with optimistic solutions, and because the follower can have multiple optimal solutions, to be on the safe side, we apply this procedure only in the case when the coefficients next to the y variables are strictly positive. So for the other situation, when will you fix the variable to the upper bound? You just reverse the situation, so the coefficients have to be negative, both in the objective function and in the whole column related to the follower's constraints. Okay, so this clearly strengthens the HPR relaxation. And the other idea that you could also apply would be related to trying to guess what is a valid upper bound for the solution of the follower. And these cuts, we call them follower upper bound cuts, could be also added to the HPR relaxation. So you take the objective function of the follower and you add it as a valid cut in which you guess what should be the upper bound. Remember that we are assuming that the follower subproblem is well defined, so this upper bound should not be infinity. So during the branch and bound search, you can probably derive tighter bounds as you are, because at the beginning, you will be assuming that the search space of the leader is the whole search space, but once you start fixing the variables at the leader level or going deeper into the branch and bound tree, then also the search space related to the x variables will get narrow and narrow, and that means that also the upper bounds that you could derive by looking into the follower subproblem will become tighter and tighter. So we will be getting locally valid cuts in this case that can be added to the MILP. So how to derive these cuts in a generic way? If you, of course, if you are solving your own problem, some practical application, you might have a lot of heuristics that you can come up with. But in a generic way, if you know nothing about the problem, if it is really for the follower, it's like a black box procedure, then one thing that you could do is to solve an auxiliary MILP in which you are actually overestimating the follower objective by replacing all the values which involve the x variables with the constants, with the worst possible constants. Okay? And then you end up with an auxiliary MILP in the y variables and with some constants that are over-restricting your follower subproblem and hence giving you valid upper bounds. Okay, so this this is now I have extracted a few important elements from this branch and cut approach, which is, as far as I know, currently the state-of-the-art approach for solving bilevel MILPs. Of course, there is still a lot of place for the improvement, and I hope that among the students who are listening to this presentation, there will be some who will take the opportunity and try to improve these results and come up with new state-of-the-art results soon. So let me show you the results of our computational study. We tested 800 instances, and for 372, the optimal solutions were known before this study, before the application of this branch and cut, and then we managed to solve to optimality almost 400 more instances. And here you can see what type of the problem of MIPS we have at the leader, at the follower level. I stands for integer, B for binary. So here we have the only group of instances where we have discrete variables at the upper level and continuous variables at the lower level, and the rest are binary instances coming from different sources from the literature. And just one chart showing you the advantages of using the follower upper bound cuts and the pre-processing. The MIPLib set of instances, the benchmark, is still the most challenging ones among the ones that we have tested. What you can see here is that after 1 hour of computing time, there are still instances, or let's say that for 20% of the instances, the final gap that you get after 1 hour is still bigger than 50%. So this is significant. So there is really a lot of place for improvement in developing new algorithmic techniques for that. So in our notation, SEP2 stands for the first family of intersection cuts, but with a separation that enforces or prioritizes to remove redundant facets from the formulation. And the plus stands, where 1 plus is for the pre-processing of the follower, and the other one is for the cuts derived from the follower upper bounds. Okay, then we also looked into the performance of the, let's call them watermelon cuts versus the SEP2 procedure. And here you can see that this separation performs totally differently depending on the structure of the bilevel problem. On the left-hand side, you have the instances that have a general bilevel structure, and on the right-hand side, you have the instances that are interdiction instances. We will talk about interdiction problems in a while. And you can see that the watermelon cuts work really good for the general bilevel structure and really bad for the interdiction instances. And so we decided that the default strategy in which we don't look into the structure of the problem, but we just simply apply in each separation stage both of them, we separate both of these cuts, is a good trade-off, as you can see, as it is represented by the blue line here. So the code that I was explaining here is available as a binary code. You can download it from the website of Marko Sinel. I will provide you the link later. And the reason I'm going here into the details is because when you download the code and when you run it with the default settings, it will be run with the mix plus strategy. But of course, you have parameters and you can change if you want to try other variants as well. So this is interesting because, as I mentioned from our benchmark set, this was the only data set of instances where we had a purely continuous follower. And we, in that case, we have employed the hypercube intersection cuts only because the other ones were not working. And here you can see the average runtimes running the mixed strategy versus the average runtimes reported in computers and OR paperback Su and Wang. So we, here the authors used a multi-branching strategy based on the slacks of the current optimal solutions that they get. And they have improved these results recently in their paper that has been just published in Nature 2020. And I believe that they have even managed to improve our running times for these specific instances. Another interesting comparison is for the instances coming from the interdiction problems, interdicting a knapsack or interdicting a click. I will define both of these problems in a while. There was a paper by Tang, Cole Smith and colleagues, published in Journal Global Optimization 2016, in which the authors developed a specific, I would say generic approach for solving interdiction problems, min-max optimization problems. And their running times compared to our running times, again, you can see here a significant difference. And again, also here, actually, these are relatively small graphs. Unfortunately, they out of 10 instances remained unsolved after 1 hour, whereas with our generic approach, we could solve them in less than a second. Okay, so now to wrap up, when we talk about the bilevel MILPs, there are different approaches. Now, I'm trying to give you an overview of the most recent approaches, computational ones. There is a lot of theory, of course, but not many implementations available. So historically speaking, in the 1990, Moore and Bard introduced the problem and derived a specific branch and bound without coupling constraints that was working either when the upper level variables are discrete or the lower level is continuous. The Negre and Ted Ralphs, they also developed many years later. As you can see, there is really a huge gap in between in terms of the developing generic computational methods, again, because of course, in these 20 years, a lot of other development has been done. So the first branch and cut comes out, again, without coupling constraints and with the integer variables at both upper and lower level. Then we have Xu and Wang with the multi-way branching. And then we have branch and sandwich algorithms for bilevel MINLPs, which can be also used in our case as well. 2017, Lozano and Smith, they also work with the discrete upper level variables, and they use a kind of a big M approximation of the value function in the extended space. So they derive something that they call extended HPR relaxation. And very recently, I'm giving you here also a link to the website of Ted Ralphs. In MathPro computations, fully fledged branch and cut approach appeared. And the nice thing about this is that it is an open source implementation. And so you can also work on it and try to extend it. In this paper, practically the authors have re-implemented most of the state-of-the-art techniques, including the ones that I was presenting today. Now, this talk was mainly based on the results that come, as you have seen, I mentioned several locations, the Wang and Xu. This is their paper from some Journal of Optimization on Multi-Way Branching. Examples that I was giving you were also available in the thesis of Xu, and also on our 2 papers from from mathematical programming and OR, in which we have introduced first the branch and bound and then branch and cut with these features. So binary code is available, and no matter whether you are using MIPS or you're using our bilevel solver, there is a specific way how you can use these solvers. Namely, you have to have a compact representation of the HPR set, which means that maybe it has to be an extended formulation, but there has to be a compact way to describe both the leader and the follower constraints that you will put together into an MPS file, okay? And then you will also provide an auxiliary file in which you will say out from these HPR formulation, which is a MIP, which variables are the variables that go into the follower subproblem, and what is the objective function of the follower. With this information, you have the complete description of your bi-level optimization problem. And so no matter if you're working on a particular application, if you are deriving your own algorithm, you could use either our bi-level solver or the MIPS solver as a benchmark tool to compare how well does your algorithm perform compared to a generic state-of-the-art approach. Okay, so that was the end of the part 2. And I would say we do not start with the questions now. We start with the questions as originally scheduled in 1 hour in our Q&A session. Okay, so and also as Martin announced in the Q&A session, which will be done at the very end, I would like to kindly ask you to post all your sessions in the chat, and then I will go through these questions and answer them one by one. Okay, now a special family of bi-level MILPs are the interdiction problems, and they have plenty of interesting applications. And for the rest of this tutorial, I will focus on these problems. We will see some examples, some interesting examples, some complexity results, and we will see how to derive, again, an efficient branch and cut procedure that can work in generic cases or in some special situations when some properties are satisfied. So what is typical for the interdiction problems, or also sometimes called interdiction gains, is that still, of course, we have 2 decision makers, and still we have a hierarchical decision-making process. The major difference is that now we have a min-max optimization to deal with, which means that both leader and the follower are optimizing the same objective, but in the opposite direction. And in addition, the leader interdicts some resources which are available to the follower. So for the simplicity, we will call them items. And in the interdiction literature, typically this activity of the leader to interdict the resources is modeled using binary decision variables. So if there is an item which is taken by the leader, then this binary variable is 1. And then this resource associated with this item is not available for the follower. That would be a discrete type of interdiction. So either this resource is fully available or not, or we can also talk about the continuous interdiction, in which the leader invests some resources and makes these, the leader interdicts and makes these resources more expensive for the follower, but still available. So from the game theoretical perspective, you could say this is a 2-person zero-sum sequential game. And it's studied a lot in the literature, mainly for the problems related to the networks, and also mainly for the problems in which the follower is solving a problem which is polynomially solvable, like shortest path or the maximum flow. And of course, today I will focus also on the more general case in which the lower level problem itself is an NP-hard problem and has to be modeled as an MILP. So if the lower level problem is a linear program, if it is polynomially solvable, a lot of specific techniques are available, but I'm not going to cover them with this presentation. So besides the interdiction gains, which are defined by having a min-max objective function, there is also another related family of problems, which we call the blocker problems. And the difference is that for the interdiction problem, we are looking for the strategy of the leader that results in the worst outcome of the follower. Whereas for the blocker problems, we want to find the minimum cost strategy for the leader that guarantees a limited outcome for the follower. in both cases, you can think of them as, you can call them attacker-defender games or defender-attacker, depending whether the leader has the role of the defender or of the attacker. So let's have a look here, for example. What happens? Yesterday, Martina already introduced the interdiction of the shortest path. So this is a funny example of, let's say, drug smuggling into the United States and Canada, and there are certain ways that are typically used by drug smugglers. So if you are the leader, and in this context, you want to attack the network of drug smugglers, you are assuming, you're anticipating that the smugglers will, in the existing network, use the shortest path to get from the source to the destination. The shortest path with whatever kind of edge costs are defined in your network. And if you want to attack them, then you might invest some resources into placing the controls or eliminating links in this network. So if you do so, obviously you don't have infinitely many resources. You have limited resources where to place these controls. And given these limiting resources, you want to invest them in such a way so that the shortest path after the interdiction is the worst possible. Okay? So this is actually maximizing the mean, max mean. It really doesn't matter if it is min max or max mean in this setting. Also, the interdiction problems that are also well studied in the literature also sometimes involve uncertainties, and these uncertainties could be either on the network characteristics or embedded in the response of the follower. Nevertheless, not surprising for you after these lectures from yesterday and today, of course, even when the follower is solving a linear program, these problems remain NP hard. Even if I just have a simple knapsack constraint or even a simple cardinality constraint. So even if I tell you I want to remove k edges from the graph in such a way that the shortest path in the remaining network is the worst possible, the problem stays NP hard. Unless, of course, k is a constant. Now, what about problems where the follower subproblem is a combinatorial, difficult combinatorial optimization problem? So the simplest example that you can think of would be the bilevel knapsack problem with interdiction constraints. So in this case, if you think of applications, you could think of two companies that have a certain marketing budget. And if the company A is the leader on the market and the company B is the follower, then the company A also dominates the market. And so whenever the company targets a certain region, then it will get the profit and the benefits from this region, whereas the company B will not be able to get any profit if A was already there. Okay? So in that sense, you could say that the set of items that we are looking at are these different regions, and that the company A, the leader, wants to minimize the benefit, the profit that the follower will receive. So in this case, the leader and the follower, they optimize the same objective function, which is the profit. The follower maximizes the profit, and the leader wants the worst outcome for the follower. Now, when we focus on the follower subproblem, we have n items, and then we say if the leader has taken the item I, then it will not be available for the follower. Okay, so it will not be able to participate in maximizing the profit. And otherwise, the follower has a standard budget constraint for solving the knapsack problem. So if I remove these constraints, then the follower is simply solving the knapsack. Bn stands for the binary decisions. Maximize the profit given the budget. However, the follower observes what happened at the leader level, and if the item is not available, the follower cannot take it. Now, what is leader doing? The leader also has a limited budget. It's a limited interdiction budget. And so the leader if he or she interdicts the item, it will cost him VI and has a limited budget, and now it wants to get the worst possible outcome for the follower. Now, as you can see, this is, of course, bilevel MILP. At both levels, at the upper level and at the lower level, we are actually here dealing with binary optimization programs. And so it falls into the specific, it has a specific structure, but it falls into the general family of bilevel MILPs. Of course, we could take the model as it is and use MIPS or our bilevel solver and try to find the optimal solution. The question is now, can we do a little bit better? Can we do a little bit more? Knowing that the connection between the leader and the follower, the only constraints where the leader and the follower are connected are these type of interdiction constraints, saying that the item of the follower is not available if it's taken by the leader. As I mentioned at the beginning, before I go on with the details how to derive specific cuts for that, interdiction and blocker problems are related. In the interdiction, we have min-max or max-min objective, and in the blocker problem, instead, we minimize the budget, and we want to make sure that the follower's objective is limited in a certain sense. So if I show you the value function reformulation for the Knapsack problem that we have seen just before, it would look like this. So for the min-max, we would introduce an auxiliary variable W, and we would hide the solution of the follower subproblem, which is the solution of the maximum of the Knapsack problem, given the interdiction action of the leader. We would hide it with this value function constraint. And that would be the interdiction budget of the leader. And here you could hide many other constraints in a general case. In the blocker setting, on the other hand, the leader will say, okay, what is the minimum budget that I have to invest so that I can make sure that the maximum profit, which is the Knapsack solution obtained by the follower, is not bigger than a given T. Okay, so these are two different settings, typically called in the literature interdiction and blocking, but if you look into them from the value function reformulation perspective, you see that if I want to solve one problem or the other using MILP techniques and branch and cut, there is really no difference. Why? Because it all comes into the description of the value function. Now the value function is usually non-convex, as we have seen, and not even continuous, and very complicated, right? However, in this specific case, we will use a technique which I call convexification by penalization to derive a convex way of describing the value function in the space of X variables. So these are two conditions which make the interdiction problems easier compared to the general situation. So one is that we will be able to convexify this function. And second is also that we will be actually able to completely hide all the decision variables which are packed into the follower subproblem. You notice also that there are no coupling constraints between X and Y in this situation. So the Y variables, they disappear completely. And this is why you can also see this approach as a Benders-like decomposition, because you will be projecting out the follower variables and you will be convexifying the function phi. Now, in the standard Benders decomposition, the function phi is convex already. You just look at the dual and you can derive Benders cuts. However, in the case of interdiction, phi is not convex per se, but it can be convexified by moving the constraints, the interdiction constraints, from the follower subproblem into the objective function by adding specific penalization multipliers. So this is the story. So let's go a few steps further. How can we do that? Okay, so now I will introduce a more general notation. And I will focus now, I hope you agree with me that it doesn't matter if we talk about interdiction or blocking, so let's focus on the interdiction part. And so we have now the minimization problem. The leader minimizes with some combinatorial structure. You can also hide here a lot of constraints, linear constraints related to the leader. And then the follower subproblem is such that the follower maximizes the payoff. It has a bunch of local constraints which do not depend on the leader. And the only connection between the leader and the follower is given by these cuts. And only in the set of variables which I will denote as n, and which refer, for example, to the items of the knapsack problem. So if the item is taken by the leader, then the variable y will be fixed to 0. Otherwise, you can introduce upper bounds. This variable can go up to a certain bound. It could be 0, 1, or it could be also higher. Okay, now we start with this problem. And of course, the first thing that we do is we reformulate it using value function reformulation. Here, there is no difference with respect to the notation. jy, as in the part 1, still denotes the subset of variables which are supposed to be integer. And of course, bear in mind that this follower subproblem can contain continuous variables as well. So the sets n, jy, and what we call ny, they can be different. So the problem reformulation with the value function as expected, right? So the leader has binary variables, and these are the only ones that influence the follower. We have a bunch of constraints at the leader level and some additional integer variables, and we introduce now the auxiliary variable to model the optimal solution of the follower. Because of the minimization, at the optimal solution, W will always be exactly the optimal value of the optimal response of the follower. Okay, so in his paper, Kevin Wood in 2010 proposed the following trick. Instead of solving the optimization problem as it is here, why don't we get rid of these constraints and add some penalization factor in the objective function that will make sure that there always exists an equivalent optimal solution for the penalized problem, which is also optimal for the original one. So if we do that, we are shifting the dependence on the leader variables, on the parametric problem, we are shifting the dependence from the constraints into the objective function. And indeed, because we are maximizing, and because the property of the optimal solution is that if x is equal to 1, y has to be equal to 0, it's only the matter of finding sufficiently large penalization that will make sure that whenever I optimize in the remaining set of variables, in the remaining constraints, which means I let y take any value between the lower and valid lower and upper bound, with all other constraints with integrality. However, if n is big enough, then there will always exist a solution of this problem such that when x is 1, I don't want to pay this penalty, so I will impose y to be 0. And of course, the question will be how to find these big M coefficients. However, but before we move into this question, answering this question, it is now crucial to see that by doing this penalization, now we practically convexify the value function phi. Why is this the case? Because now the set of feasible solutions over which we are optimizing is a polyhedron, okay? You can look at the convex hull of all extreme points satisfying these constraints. And now the objective function for a given x and for the given m is a linear objective function. So optimal solution, no matter which x you plug in, will be one of the corners of this polytope. So in this case, of course, then you can look at the extreme points of the convex hull of y, and then you can equivalently restate 21 in this way. So phi of x is now the maximum over all extreme points, or over all points from the set y hat, in which I plug in now the value of y hat, I have the values of m, and x is the variable now. So what is this now? Well, this is the maximum of a finite set of linear functions. So it is a convex function, phi. It's a convex piecewise linear function. Okay? And so this is this convexification by penalization, which means that now we have here a convex MINLP, if you want, right? Because we have here a convex piecewise linear function, and the rest is just an MILP. And this is the way to go towards developing a branch and cut approach. So in the branch and cut approach, you will of course start as usual by ignoring the value function constraints, and then you will be separating them on the fly. So this is the idea, and observe now that all these constraints, they are purely linear functions in X, which means that we have really projected out the variables from the follower subproblem. What is the cost for this? Of course, each time we have to separate a cut of this form, each time we have to find one of the extreme points of this set. And if this set contains integrality conditions, well, that means that each time we have to solve an MILP to derive a new valid inequalities of this form that will be added into the model. Okay. So, of course, the question is, how do we get these values of big M? Because the strength of your formulation will depend a lot on them. So just to summarize, so this is the MILP reformulation that looks like a Bender's reformulation of the original problem, in which now the follower variables do not play any role, and we have, unfortunately, an exponential number of constraints, 22b, and separating them, as I just explained, requires solving the follower subproblem, which can be, or is in most of the cases, an NP-hard problem. Nevertheless, that can work well in practice. Okay, so to answer this question, how to find these big M's, I will give you some results that are not valid, that are not always valid, that are valid for the problems, interdiction problems that satisfy monotonicity property. So let us now complicate the notation a little bit more, and let us look at the follower subproblem by separating the set of variables into those which are influenced by the leader and the rest, because the follower can be really an extended formulation in which we have the items from N that can be restricted by the action of the leader, and then there will be some other items, and we call them from the set R for the rest. And now you can restate the same problem just by separating these two subsets of variables. Now, what is important is that in this case, when we define the monotonicity, we really do not care about the other variables. We only care about the variables that can be restricted by the leader. And so this is the set Qn. And the monotonicity property that we require to be satisfied in this case is the following one. We say that if I have a solution whose coordinates yn satisfy the integrality constraints and are a feasible solution to this problem, then I want that also any other solution which is in coordinate-wise smaller than this one, sorry, y hat, any other solution which is between 0 and y hat is also feasible. So the simplest case that you can think of is a knapsack problem. Knapsack problem satisfies, when I look into the follower description, satisfies the monotonicity property. Why? Because whenever I have a feasible solution of the follower, y hat, so I ignore this, say it doesn't exist, then of course any other subset of items is also feasible, right? So in general, you could say if the follower is solving a knapsack problem, it satisfies the monotonicity property. So if you assume that all the coefficients, the whole matrix Qn is non-negative, then the variables and of course the coefficients in the objective function are also non-negative, then we have this monotonicity property satisfied. Now, what are the other problems where you have this monotonicity property, which is valid? Well, if you are solving a matching problem, for example, then matching, any maximal matching is a feasible solution, but then also any subset of edges of this matching is also feasible. Or if the follower is solving a clique problem, then if I have a clique, then also any subset of this clique is also feasible. So if you think of combinatorial structures, then basically monotonicity property means that we have the feasible set of the follower forms an independence system, or that the hereditary property holds. Okay, and now you can extend this property. So it only has to hold, the hereditary property only has to hold on the subset of variables influenced by the leader. The other variables are here, but are not affecting the property that we are requiring. So if this is the case, then first of all, you may ask, is then the problem easier to solve or not? Even if the follower is solving a pure linear program, is the problem maybe polynomial or not? Well, the bad news are that even if the follower is solving a pure linear program, satisfying this monotonicity property, then the problem is still NP-hard. And Zenclusen showed it by looking into the interdiction of the matching, and Dinitz and Gupta looked into the interdiction of set packing. And so other examples I already mentioned, like maximum clique problem. You can also think of the price collecting or orienteering problems in the logistics, multidimensional knapsack. They all satisfy this monotonicity property. In general, even with monotonicity property, the knapsack interdiction is already sigma 2p hard problem. So again, bad news. Nevertheless, we come back to our question, and this is the result that we have published in Infant Journal Computing last year, again together with Matteo Fischetti, Michele Monaci, and Marco Sinel, in which we have derived the result that tells us that the big M's can be pretty tight in case that the follower subproblem satisfies this monotonicity property. And indeed, in this case, our interdiction cuts can be written in this way. So you have the variables that come from the extended formulation, which are the rest of the variables, plus those which are interdicted by the leader, and then the big M's that come here are just the values of dj. So this is good news, because these cuts are really tight, and then you can show that under certain conditions, they are also facet defining, and you can separate them in a branch and cut fashion. So now you see two alternative ways. One is to use intersection cuts and the whole machinery that I was describing at the beginning, or to derive this specific branch and cut approach with a very specialized separation procedure. So if I'm solving a knapsack problem, for example, how will we separate these cuts? So we will get the current solution of the current node of the branch and cut tree. And if the solution is integer, then we will simply remove the items which are taken by the leader, and we will solve the knapsack problem on the remaining items. Okay, so that will give me a point, a feasible point from the follower space, but not necessarily an extreme point, because the extreme points will be corresponding to the maximal packing of the knapsack. So to get to the extreme point, then we will try to enlarge this knapsack solution by adding additional items which are taken from the leader, but anyway, they could improve and tighten the cut. So I don't have slides explaining this, but you can have a closer look into our paper to see, but it is not difficult to see that the cuts which are associated to the maximal packing of a knapsack, maximal solutions, they dominate the other ones, which are, because of the monotonicity property, they dominate the cuts of the subsets of the packings. And if you talk about the implementation in using the general purpose solvers, that means that you will get a fully fledged branch and cut approach by implementing lazy cut separation and separating these cuts only at integer points. If you separate the cuts at fractional points as well, you will of course tighten the formulation earlier in the branch and bound phase and probably reduce the number of branching nodes. The other advantage compared to the general purpose bilevel approach that we have seen before is that now you know that the follower is solving a knapsack problem. So you know that you have plenty of efficient procedures for solving the knapsack, like the dynamic programming procedure or other more advanced combinations of dynamic programming and branch and bound and so on. Also, if you're not focusing on solving the knapsack problem, but another problem that satisfies the monotonicity property, you might have at hand more efficient specific algorithms that you can employ for the separation procedure rather than just focusing on solving it as a black box MILP. So to summarize, it doesn't come as a surprise that developing a branch and cut approach for this specific type of problems will beat the generic approach that we have seen before. I'm skipping now these details. It is just to show that these cuts can be lifted if they are not fastly defining, and you can exploit additional dominance properties between the columns if there are any in this monotonicity setting. So what can we see now? As I announced already, it really doesn't come as a surprise that the branch and cut developed in this way is better than generic approaches. Before that, I'm showing you just comparison to the cutting plane approach versus the branch and cut. What is the difference? In the cutting plane approach, you would solve HPR relaxation. You would solve, no, it's not an HPR relaxation in the classical sense, right? So you would solve the relaxation of the problem without the description of the value function as a MIP. Then you find one cut by solving another MIP, you put it back, you solve the MIP again, and so you go back and forth. Instead, what we are using here is the branch and cut approach, in which we are separating the interdiction cuts inside of the branch and bound tree. So it's this similar difference like the old style implementation of the Bender's decomposition versus the new one where we call it branch and Bender's cut, versus the old style where we had solve a MIP, find the Bender's cut, and so on. And so you can see that there are significant differences in the performance, which comes from the fact that the bounds that you get at the root node by just solving the LP relaxation and adding these cuts are much tighter, so you do not really have to branch a lot, and you save solving a lot of MILPs that you are solving in the cutting plane case. And that was an alternative procedure proposed also in Infant General Computing by Caprara and colleagues. Now, when it comes now to the Mix++, our bilevel solver, this is what you can see. So you see improvements of several orders of magnitude. And again, coming from the fact that first you have a tighter formulation, problem formulation, because these interdiction cuts are very often facet-defining cuts. And second, because the separation procedure for them is much more efficient than the generic procedures proposed for the mix plus plus. Okay, and then I have one more problem that I want to show you, which is the click interdiction problem, which is another problem that satisfies these monotonicity properties, but is now defined on graphs. So what is the click interdiction problem? You can also see it as a Stackelberg game, in which the leader is the one who wants to remove the vertices from the graph in such a way that the click number in the remaining graph is the worst possible. Okay? So the leader has a limited budget, wants to remove, for example, if the budget is only 1, so then the leader can remove only 1 vertex from this network. So in this network, there are many max clicks, and for example, one of them is shown with the red vertices and has the size 5. So the click number is 5, and if the leader is given budget of 1, the leader can remove the vertex 8 and reduce the click number to 4. And one possible click that remains in the interdicted network is depicted again in red. Another example, for example, if the leader has a little bit bigger budget, like if the leader can remove 2 vertices, even after removing 2 vertices, the click number in the remaining network remains 4. But if the leader can remove 3 vertices, the click number remains 3. So you can see it as a bilevel optimization problem. The decision of the leader is which vertices should I remove. The objective function of the leader is minimize the click number in the remaining graph. The follower, on the other hand, the follower is just solving the max click problem. So the follower is calculating the click number on the interdicted graph. And again, we can model this problem as a bilevel MIP, or actually bilevel 0-1 IP, okay? Because the follower subproblem satisfies the hereditary property with respect to the objective function, with respect to the items which are interdicted by the leader, then we have the same results that we have seen for the Knapsack problem that can be also applied for the click interdiction. Okay, so the leader removes the items. The items are now the vertices. The follower finds the click, and the monotonicity property is satisfied because any click, any sub-click of the given click is also a feasible solution for the follower. So in a similar way, you can come up with a Benders-like reformulation that will look as follows. So now you minimize W, and W should be the maximum click, or let's say the click number of the interdicted graph. You use XU variables, binary variables, to decide whether the leader is interdicting a vertex or not, removing it. The leader can remove at most K vertices. You can also replace this constraint by the budget constraint if removing vertex A is more expensive than removing vertex B. Doesn't matter. And the most relevant constraints that describe now this problem, remember, in the space, all in the space of X variables, without looking at the MIP of the follower, are these ones. So what are these? K, the calligraphic K is the set of all clicks in the original graph. And so for any click, whenever I take a click of the graph, what we are saying is the following. If the click number in the interdicted graph is W, and I'm looking at a click of size K, then I have to remove from this click at least XU nodes to make sure that the optimal solution is W. So if the optimal solution is 3, and I have a click of size 5, what I'm saying is is that I have to interdict at least 2 nodes out of this clique. Again, we have here an exponential number of constraints, but not only that, but separation of these constraints requires solving a maximum clique on the interdicted graph, which is again an NP-hard problem. Nevertheless, again, because this problem is a very specific one and very efficient, algorithms exist. You won't solve the maximum clique as a separation using an MILP. You will use a state-of-the-art algorithm. In this case, we use the state-of-the-art clique solver from Pablo Sanz-Secunda and colleagues. And we started with this formulation, but then we also show that these cuts are facets under very mild conditions, and if not, they can be efficiently lifted. And using the dominant structure, you can derive also efficient graph reduction techniques and solve these kind of interdiction, this specific interdiction problem very efficiently. Also, results of this paper have been published. This is a joint work with Fabio Forini, Pablo Sanz-Secunda, and Sebastian Martin last year in IJOR. So let me just show you some computational results again. Now we are comparing this branch and cut approach with the mix plus, and for different Erdős-Renyi graphs that we have generated with different properties. And what is striking here is the quality of the root gap. The quality of the root gap obtained using this Benders-like reformulation versus the quality of the root gap obtained using the intersection cuts. Again, not surprising, because the intersection cuts, they work in the space of the X and Y variables. They only use generic intercuts, whereas here we reduce the space and we have constraints which are facet defining most of the time. And then you can see that also we can solve many more instances than the generic approach. And then we can also go on, we can extend it and solve much larger graphs, even graphs with 2.5 million of edges, for example. Well, thanks to the super efficient procedure, because this here column is showing you what is the time needed to calculate the clique number in these graphs. So even though the graph is huge, it requires only 1 second to find the clique number. So we can indeed afford to separate these inequalities on such large graphs. Of course, we do a lot of pre-processing. Here you can see some numbers regarding the elimination of the number of nodes that we can eliminate before running the branch and cut. Okay, so I think we are approaching now the conclusions. So what have we seen today in these 2 sessions? First, a generic approach, or an overview of generic approaches to deal with bilevel MILPs. And these are based on the basic branch and bound procedure enhanced with intersection cuts. And then we saw that we can do much better if we know our problems well. And in particular, if we are solving interdiction-like problems, then we can derive specific interdiction cuts that can be separated faster and so on. Okay, and we have also seen that these interdiction type cuts can be also used for blocker type problems as well. Now, as I said, there is still a lot of space for improvement. And some of the interesting questions that some of the students listening to this presentation today might consider for their research could be, for example, finding other bilevel free sets, or, for example, finding a better way to combine multi-disjunctions with bilevel free sets, deriving tighter cuts for the generic case. Generic case is really, really tough. But then the possible nice direction for the research would be, what if we now move into the nonlinear mixed integer bilevel problems? And Martin Schmidt, with his research team, he's working a lot in this direction. So I'm also looking forward to some results coming from his team. Of course, the first natural question would be, what happens if we are dealing with convex objective functions, or if we have convex constraints in combination with MINLP, of course. Bilevel pricing problems are also very tough. Martin introduced these problems yesterday. And as you have seen, first you have, for these price setting problems, you have bilinear terms in the objective function. And then you have bilinear terms also in the objective of the follower. They turn into linear once you fix the leader decisions, but nevertheless, this is also, there is also a lot of space. And as far as I know, there is no generic approach to deal with this type of problems so far. And then the next interesting question is, what about multi-level optimization problems? What if it's just move to the free level? For the interdiction, it will be much, much easier. There is already a lot, some literature available. That will be something which is known in the literature as defender-attacker-defender model, where we still have actually two players, but in free stages, like free stage decision-making process. What I didn't mention, but I think it has been mentioned by Martin yesterday, is that it is not that we have to focus ourselves only on one leader and single follower. All the concepts that have been shown today can be also easily translated into one leader, multiple followers, under the assumption that the followers are acting independently. If there is the dependence between, if the followers influence each other, then it's a very different situation. And I assume that Didier will talk about that tomorrow. So I have a huge list of literature that I used for these slides. We will share these slides. Martin will share these slides with you on the website. And this is practically where I would like to stop my presentation. I think we are on time. And you have some time now for a short coffee break before we meet again in the Q&A session.